Alright, this geometry video is from chapter 2 and it's going to cover two sections. They're kind of smaller and they go together nicely. Those sections are 2.3 using deductive reasoning to verify conjectures and 2.4 biconditional statements and definitions. At any point during this video, feel free to hit pause if you need a moment to write more things down, or if I'm going a little too quickly, because obviously some of it I've pre-written that you haven't written. So don't be shy to hit pause, write down what you need. I also don't mind if you're at home, you can also hit rewind if you need to hear something again to help it make more sense to you. So just use this video at your own pace of what works for you. Alright, our objective is, as the student, I can apply the law of detachment and the law of syllogism in logical reasoning, and I can write and analyze biconditional statements. Now, this bottom part will be our objective for 2.4, whereas the top part will be our objective for 2.3. You'll know that we switch to 2.4 when suddenly we start talking about biconditional statements. That'll be your cue. But it's okay if all your notes are together for these two, as long as the title in your notes includes both. Alright, let's talk about some vocabulary. That objective included some words that we might not be familiar with just yet. So let's start with deductive reasoning. Deductive reasoning, as I've hinted to you in the past when we were talking about inductive reasoning, deductive reasoning is think Sherlock Holmes, think facts and logic, think definitions, think math properties, think facts about, let's say, if you're not sure if there's a school dress code policy. If you watch students walk by and you see a pattern, that's inductive reasoning, where you think there's a dress code policy. So that's inductive reasoning. But as soon as someone shows you that handbook and shows you the actual policy and you're given a fact, that's facts and logic, that's deductive reasoning. Then you can prove and know for sure that there's a school dress code policy, as an example. So deductive reasoning, the official definition is the process of using logic to draw conclusions from given facts, definitions, and properties. So just know there's two types of main reasoning. There is inductive reasoning, which is patterns, and there's deductive reasoning, which is facts and logic. This whole video is going to be all about deductive reasoning. Alright, now there's two main laws of using deductive reasoning. The first main one is the law of detachment. The law of detachment is the one that we often tend to overthink sometimes. In symbol form, it looks like this. If you're given a regular if-then statement, meaning, remember this is pronounced if P, then Q. That's what those symbols mean. So if P, then Q, meaning P causes Q. That's why it's pointing at Q. Anyways, if you're told the statement P then Q is true, and P is true, meaning it actually happens, then you can logically conclude that the conclusion will also happen, or Q is true. So let me give you an example. Let's say a guy tells his girlfriend, hey, if I get paid this week, then I will take you to the movies. So in that example, if I get paid this week, that's the hypothesis, because it depends on whether or not he gets paid. So if he gets paid. Alright, so the statement is, if I get paid this week, then I'll take you to the movies. Alright, later this week you find out he got paid. Remember, getting paid was the hypothesis. In other words, the hypothesis has happened. So if he got paid, you can logically expect and conclude that he will do Q, which was take her to the movies. So her going to the movies depended on whether or not he got paid. But if he gets paid, you can conclude it. So I want to be clear, it's when P happens, or when the hypothesis happens. The law of detachment does not work in reverse. Q does not cause P. There's not an arrow pointing at P. For a regular law of detachment, it's for a regular if-then, P causing Q. Make sure you're with me on that. It does not work backwards. Alright, so before I talk about the law of syllogism, I want to go ahead and, if you've already written it, great. We're going to go ahead and do an example of using the law of detachment, and then we're going to come back to the law of syllogism. Alright, go ahead and take a minute to copy down this example. This is going to be an example of using the law of detachment. You will be given a statement, so an if-then statement, and then you'll be given usually one more piece of given information. So, in this question, hit pause, go ahead and write it down, then we'll talk about it. Okay, so you'll be given an if-then statement, then you'll be given some kind of facts of some kind, and then the question will either say, what can you conclude based off of this happening, or it'll say, hey, verify this. Is this true? So sometimes it does a little bit of both. It'll ask you to conclude, or it'll say, hey, verify a conclusion. Or in this case, it could be a conjecture because it has not been verified yet. So let's do this. When you break these down for law of detachment, it's going to help if you identify who is the hypothesis, who is the conclusion. So remember, the thing that comes after the word if, that is your hypothesis. So in this case, P is two segments are congruent. The hypothesis, remember, does not include if. It includes the words after if. So we found P. And you'll remember Q is the conclusion, and that's what comes after the word then. They have the same length. That's going to be Q. That's going to be our conclusion. So in other words, we were given an if-then statement because we now know, okay, P leads to Q. Remember, that's what that means. All right, so the law of detachment told us we're looking to see if P will happen, if the hypothesis will happen. That's what we're looking for. So we come back to this example. They have one more piece of given information. Let's see what it says. This given information says line segment AB is congruent, remember the symbol for congruent, to line segment XY. Even though our statement didn't name line segments, it just said if two segments are congruent. We'll tell you what, we got a line segment, and this says congruent. So what this means is this means P happened, or P is true. So now that the hypothesis has happened, the law of detachment tells us we now can expect for the conclusion to happen, meaning they will have the same length. We can expect that. So that tells us the law of detachment allows us to conclude, therefore, line segment AB and XY do have the same length, because that's using the definition of congruent. Of being congruent. Alright, so therefore the length of AB is the same as the length of XY. Or if it had just asked you, was this statement true? If they had just asked you that, you could say, yes, it is true. Valid, so you could say true, you could say valid, and it is a valid use of the law of detachment. I'm just going to write LOD for its abbreviation. So if they ask you to confirm if it's true, you can because it is a valid use. Now, remember, this has had nothing to do with even if you think the statement is true, we're relying on just the law of detachment here. We're not talking about whether a statement's really true or not. We're talking about if you're told it's true, if it's given information. We're talking about how to use the law of detachment to make conclusions based off of that. Alright, so take a look at this example. Go ahead and hit pause and write it down first. This is all given information. Go ahead and hit pause so you can write it. Alright, so in this question we're going to see, is this an example where we can use the law of detachment? The given if-then statement says, if you get 3 tardies, then you will get detention. Go ahead and underline the hypothesis and the conclusion if you think you already know what they are. You should have underlined getting 3 tardies as the hypothesis and getting detention as the conclusion. Alright, so that's our if-then statement. We've identified P, then Q. Now, the given information goes further. Not only were we given the if-then statement, we were then told, okay, something has happened. Lauren has detention. So now you have to decide, can you use the law of detachment? And remember, the law of detachment told us that it's the P that causes the Q. Meaning, if the P happens, we can guarantee the Q will happen assuming the original statement was true. Alright, so Lauren has detention. You'll notice, getting detention, that was the blue. That was the conclusion. So in other words, Q happened. That's what that means. Alright, so Q has happened. So remember, the law of detachment I told you only works forward. You cannot guarantee Q will cause P. But since we're told this is true, we can guarantee that P causes Q. So this statement, I understand logically you may think that she got detention because of those 3 tardies, but technically if you're picky, you could say, well, anything can give you detention. Maybe she did something else to get detention. And so we can't guarantee that her having detention was because of those 3 tardies. It does not work in reverse. So this is an invalid use of the law of detachment. We cannot guarantee this is true. So in fact, we don't even know if this is true. And even if it was true, we still couldn't defend it using the law of detachment. Sometimes you will have a true statement. You just still can't defend that true statement with the law of detachment if you went in reverse like this. So just keep that in mind. Alright, so now we're going to go back to the top. We're going to talk about the law of syllogism. That's our last law of deductive reasoning we're going to talk about. And in fact, that's basically the end of the 2.3 notes. Alright, so law of syllogism. think of it as having a middleman. I'm just going to already put that out there. So check this out. If P causes Q, if P leads into Q, notice that arrow pointing, if P leads into Q, and Q leads into R, what the law of syllogism tells us is skip Q. Go straight from P to R. That's what it's basically saying. Cut out the middleman. That's how I describe it. The middleman in this case was Q, and so go straight from P to R. That's what the law of syllogism tells us. And so I can give you a pretty basic example of it, and then we'll do a couple other examples of it. Before I do, I do want to make sure I point out, this only works when it's going in the same direction, meaning if you're given a statement that leads into Q and that same Q leads into something else, that's when it works. So a silly example would be something I'm about to jot down. You don't have to write down this next one, I'm just going to kind of give it to you visually. Alright, to help make a point, I'm not even going to write this in proper English. You don't have to write it down. I just want to help you see the subjects. But I'm going to say the sentence out loud. Imagine you had a sentence that said this. If the animal is a dog, then it is a mammal. Period. Next sentence. If it is a mammal, then it has hair. So you'll notice dog was used here. It was the first subject or thing discussed. We can call that P. It being a mammal is Q, because that's the conclusion. If it's a dog, then it's a mammal. So that's the stuff you already know. But notice this new sentence, they're using mammal again. Well, we've heard mammal before, and we called it Q. So you're going to call it Q again. But now they're talking about it having hair. That's something completely new. That's not the dog statement. That's something new. So because it's something new, we're going to give it a new letter. We're going to call it R. So this is what I mean when I say P leads to Q. I don't know why that's green. And then Q leads to R. So in other words, if it is a dog, then it's a mammal. If it's a mammal, then it has hair. We're going to cut out the middleman. We're going to make a logical conclusion using the law of syllogism. We're going to cut out the middleman altogether. The middleman was mammals. We're going to go straight from P to R. And in other words, to put it out loud, we're going to say if it's a dog, then it has hair. Like I said, you didn't have to write this one down. I just wanted you to kind of see it. If it's a dog, then it has hair. If you really want to write it, you're welcome to. Otherwise, I just wanted you to see it because we'll do examples after this. And now, just remember, even if it's not technically true, if you don't think it's true, it doesn't matter. You're going to trust what they told you. If they told you this was given information, and given information it means it's true. So, assuming this is true, we can make this conclusion. In this case, I think you would agree most dogs do have hair. I'm sure there might be a couple technicalities out there. Like, I don't know if there's a Mr. Bigglesworth version of dogs. Who knows? Alright, so take a moment to copy down this example. Go ahead and hit pause and copy it down. Two pieces of given information, a given sentence and something you're asked to verify. Or maybe they wouldn't even give this to you, and they would just say if, and they might ask you to finish the sentence. Go ahead and hit pause and write it down. Alright, so in this example of using the law of syllogism, you're given more than one if-then statement. Sometimes they will give it to you as an if, a then, an if, a then. Sometimes they'll give it to you in order like this. So let's watch it. If the measure of angle A is less than 90 degrees. Okay, that's the first thing they've talked about. That would be P. Then they go on to say, then angle A is acute. Alright, well that's a new piece of new discussion to talk about, new subject. So that's Q. But look, it keeps going. Then, so in other words, if it's less than 90, then it's acute. Then it is not a right angle is what it's saying. So that's a new piece of information. So it is not a right angle. That's going to be R. So that's what I mean by P, Q, and R. So this one's kind of literally P leads into Q, which then leads into R. So this is kind of what I mean to where you can cut out that middleman of Q. So visually, if you wrote out P leading to Q and then Q leading to R, even though in this case Q only happened once, you can still write them separately like this. So we can cut out that middleman, cut out the Q, and go straight from P to R. That's what we can do. P leads to R. In other words, if the measure of angle A is less than 90 degrees, then it is not a right angle. And if you look down here, that's what it says. If this was given, they asked for you to see if it's true, you could hit mark it true. Or if they wanted you to conclude this on your own, fine. You're allowed to conclude this on your own because this is a valid use of the law of syllogism. Alright, go ahead and hit pause and write down this example. You're given a statement and you're asked to verify something. Or again, the instructions may not have asked you to verify it. They may have asked you, what can you conclude? But in this case, I want to help you avoid a common pitfall. Oops, hint, hint. Alright, so this is an example where we're going to try to use the law of syllogism. And I already kind of gave away up at the top. Let's pretend that wasn't there. Alright, so given information. If a number is divisible by 4, I'm just abbreviating a number right here. If a number is divisible by 4, so that is P, that's your first subject, then it is divisible by 2. Okay, that's the second thing they said. That is your conclusion. Being divisible by 2 is the conclusion. Meaning, if it's divisible by 4, that's causing it to be divisible by 2. So, and then you're given one more piece of information. You're told if a number is even, then it is divisible by 2. Well, we haven't mentioned anything about even yet. So, a number being even, that's going to be R, because we haven't mentioned anything about even. But then it says it's divisible by 2. And you'll remember, divisible by 2 is what we marked in blue. It's what we marked as our Q. So being divisible by 2, that's Q. Alright, so now we've identified everything. P led into Q, and then R led into Q. So let's write that in simple form. So I went ahead and wrote it at the top. P leads into Q, and R also leads into Q. So now it's asking us to verify this conjecture. If a number is divisible by 4, then it is even. Well, you'll remember, being divisible by 4 is P, then it is even. Being even was R, so we're going to mark that as R. So they're telling us P going straight to R. Well, that does ring a bell with the law of syllogism that we talked about, where we talked about cutting out the middleman in this last example. P going straight to R. So this has a chance. We're used to seeing P go straight to R with law of syllogism, so it's possible. So now we just need to find out, is it valid? Can we say this? Some of you might be thinking, well, yeah, this is true, because that is true. If something is divisible by 4, you can guarantee it's an even number. For example, 4, 8, 12, 16, 20, 24, 28, all of those numbers that are divisible by 4, even negative 28, negative 20, they are all even numbers. So I agree, this statement is technically true, and I'm not going to argue with you on that. However, the problem is we cannot prove this statement in this situation by attempting to use the law of syllogism. Because the law of syllogism, you'll notice Q was not the middleman right here. I agree they have Q in common, but they didn't connect through Q. P led to Q, and R also led to Q. Whereas you notice they don't go in order. So they need to go in order like they did in our previous example on this one, where P led into Q and Q led into R, or our silly dog example. That one. Oh, jumping ahead. Alright, so what that means is this is an invalid use of the law of syllogism. So a common pitfall to avoid is, even if the statement they say truly is true because you know the skill or you know the knowledge that it's true, you still have to check if it's a valid or invalid use of the law of one of those, either syllogism or detachment. So be mindful of that. Being true doesn't necessarily mean you use the valid law of deductive reasoning. Alright, so that's going to be our last example for the deductive reasoning. And so now we're going to talk about biconditional statements. And when we're done, we'll see how much time we have. I will look into doing some homework examples. I'll try to include a few similar problems, make sure you're clear. Alright, so go ahead and hit pause and copy down the notes you see on this screen. This will be the last of your vocabulary. You need to know what a biconditional statement is, and I want you to know what makes a really good definition, especially a math definition. So go ahead and hit pause and write this, and feel free to space yours out a little more than I did. I know I ran out of room over here. Alright, so biconditional statement. You know you have a biconditional statement when you combine a conditional statement with its converse. In other words, if you were to combine the forwards version, which is just the regular if-then, with its converse, which remember is the opposite order, we switch them. So if you were to combine those at the same time, notice you got an arrow pointing both ways. That is a biconditional statement. That means you're stating something that you're claiming goes forwards and backwards. Like, in other words, P causes Q and Q causes P. That's what you're saying when you write it this way. The way you'll see it written, or the way you can translate it to words, you no longer use the word if and then. You say it like this. You say P if and only if Q. So an example of that is what I have down here. It says a figure is a triangle if and only if it has exactly 3 sides. And you can say and 3 angles. Sure. That statement's true forwards and backwards. Wait, I keep saying true. We're not talking about true right this second. We will in just a moment. But that statement, we're saying if it's a triangle, it causes it to have 3 sides. Well, if it has three sides, that's going to cause it to be a triangle. So it can go in either direction. So because of that, it is a biconditional statement. So if and only if, meaning no deviation in both directions, meaning no exceptions, no counterexamples, if they're claiming it's true. So speaking of being true, if a biconditional statement is going to be true, that means it must be true going forwards, and it must be true going backwards. And that's what I kind of already alluded to that when I talked about these. If it's true forwards and backwards, such as this statement, meaning if it is a triangle, then it has three sides, well, that's true. Then we could say if it has exactly three sides, then it's a triangle. Well, that's also true. There's no counterexamples to those two statements. So the two inverse and converse of this are both true. Because of that, it is a true biconditional statement. And the good thing is, true biconditional statements, these make the best definitions when you're trying to describe something. So a lot of times, the way you hear a geometry or even a math concept is a great way to be a definition, is if it's a true biconditional statement. So we're going to define definition. It's a statement, I forgot the letter T apparently. It's a statement that describes a mathematical object, and it then can be written as a true biconditional. So bear that in mind for quality definitions. They are true forwards and backwards. I want to take a moment to include this. This is straight from your 2.2 notes, so you don't need to write this down again. But I want to remind you, just in case you're not clear, what does it mean for something to be true? Remember, if a conditional statement is true, that means the hypothesis guarantees the conclusion will happen. You can't think of any exceptions. It guarantees it, that if this happens, it guarantees this will happen. However, if the hypothesis happens and then the conclusion does not happen, remember, true means happened, not true means didn't happen. So if the hypothesis cannot guarantee that the conclusion will happen, so if you can find a counterexample, that means it's false. So keep that in mind when deciding if these things are true or false, because you will have homework questions that'll ask you, it'll give you a statement, and it'll say, is it regular if then? They won't call it that. They'll say, is the original conditional statement, is it true? Yes or no? Then it'll say, write the converse, or it'll give you the converse, and it'll say, is the converse true? And you'll say yes or no. Now, if they're both true, what we just talked about, that means it is a true biconditional statement. So then you would say the biconditional is true if both the forwards and backwards are true. So bear that in mind. Also, I'm going to come back to this bit right here because you're going to need this for some of your homework questions. So I'll mention that in just a moment. Alright, so I'm going to jump into some homework examples, and before I do, I want to let you know, if there's anything you don't have time for in class, I will be posting, this video will be posted on my YouTube channel. You're welcome to check it out, and if you want to see more examples, or you just want to go further, let's say you didn't get as far as you want to get in class, so you are always welcome to do that. Alright, so I'm going to give you a disclaimer. For many of your homework questions, you're going to find that many of them will be random made-up statements. There'll be a little bit of nonsense, and that's kind of on purpose because that's Alex's way of generating random statements. But the good news is it forces you to use the logical rules we just learned, and you won't be able to rely on what you think is your common sense. So common sense is a great thing, don't get me wrong, but like for example, look at this first sentence in this sample homework problem. This first sentence says, given, meaning assume it is true. If Omar likes the milkshake, then the play is a success. I think you'll agree, what on earth does a milkshake have to do with the play being a success? But if you're told to assume it's true, you got to roll with it. So the hypothesis would be Omar liking the milkshake, and the play being a success would be the conclusion. So if that's given information and you're asked what else must also be true, you cannot use your common sense with this. Maybe you'll make a little silly story in your head, but that's not what we want you to rely on right now. Just use what you know. Use what you know about logically equivalent statements. For example, if you analyze this one, you see that they switch the order. They put Q, then P. So this is the converse. Well, we can't guarantee that the converse is equivalent to the original regular if-then, because you'll remember that might ring a bell from our notes that we have in 2.2. Converse is guaranteed to be equivalent to inverse, but it's not guaranteed to be equivalent to regular if-then, your regular original conditional. However, your contrapositive is guaranteed to be equivalent, meaning it will have the same truth value. So if you're told that your regular if-then is true, meaning the milkshake and the play being a success, if you're told that's true, that means its contrapositive is true, meaning negate Q, so instead of being a success, not a success, negate P, instead of liking the milkshake, not liking the milkshake, and you switch the order. Don't forget we switch the order. That's the contrapositive. We can guarantee that that is equivalent. So if the original is true, we can guarantee the contrapositive is true because they are logically equivalent statements. It has nothing to do with whether we actually know anything about these statements that say they're true. So we cannot guarantee that the converse and the inverse are true, because you'll notice this last one is just the inverse of the original, meaning they negated both sides, but they did not change the order. So I just want you to bear that in mind. You're going to use your rules about logically equivalent statements, and you're going to use what you know about the law of detachment and law of syllogism. Now, you can write these examples down now if you prefer, or you're welcome just to look at it online, or just think about it. I really just want you kind of to practice it. So think about these and see if they make sense for you. Take a moment to do that. If you need to pause to think or write something down, go ahead. Alright, so in the second part, you're given, if an instructor hates to fly, then the wall has been painted. Now again, I know those are nonsense, but let's ignore that. So P leads to Q. Okay. Now it says if the wall has been painted. Okay, so they re-mentioned the first one. So that's Q again. Then Sung is calling a timeout. I don't know what that has to do with it, but I'll stop bringing that up. In other words, if the wall has been painted, he's going to call a timeout. Well, calling a timeout is something new, so that's R. So you'll notice P leads into Q, and then Q is used again, and Q leads into R. That tells you they're probably going to be activating the law of syllogism. So look out for the one that's using the law of syllogism. And if you look at the middle one, look what it says. The middle one cut out the middleman. It cut out the walls being painted. The middle one says, if our instructor hates to fly, which was P, then Sung is calling a timeout. So I'll help you color code that if that helps. If our instructor hates to fly, and then purple was the timeout. So they went straight from P to R using the law of syllogism. So that one is completely true because it is a deductive conclusion. Now, the first one, if Sung is calling a timeout, well, that's R. Then our instructor hates to fly. Well, that's P. So in other words, they're trying to go from R to P in that first one. However, the law of syllogism, I mentioned it backwards. I mentioned it earlier, does not work backwards. You cannot go straight from R to P like that. You can go from P to R because it works going forwards, but we cannot guarantee it works going backwards. That's why that first one's false. And finally, the last one says if the wall has been painted, then our instructor hates to fly. In other words, that's the converse of the first statement, and we cannot guarantee that the converse is logically equivalent to the original, just like we said in the previous question. Alright, so the last one I'll do with this is given information. If it says, if I am in my first period class, then Layla heard the radio. Well, first period class is the hypothesis. Layla hearing the radio is the conclusion. And then it goes on to say, I am in my first period class. In other words, that's P. P has happened, meaning the hypothesis is true. Well, the law of detachment tells us if the hypothesis happens, we now know that the conclusion will follow. It will cause the conclusion, so Q will follow. So look for the answer that mentions her hearing the radio. So that's this one. This is the one that's going to tell you using the law of detachment. So keep that in mind. It's kind of like the if he gets paid, then he'll take her to the movies. Well, he got paid, so he had to take her to the movies because that was the logical conclusion. Alright, so this was an example of talking about truth values. So this would be more of a 2.3 question, but I wanted you just to see it because it'll be in the same homework you'll be looking at for this assignment. I'm going to do at least one, maybe two more examples with you, just to make sure we're clear. Alright, take a look at this similar homework problem. The instructions are down here. It says the table below gives the material of each item in Heather's jewelry box. These are the only items in Heather's jewelry box. In other words, I want you to use her inventory. That's how you'll decide whether something is true or false. Do not use what you think you know about the real world. Think about, just limit it just to what she has. So in other words, use this table to determine any truth values. So let's look at the original given statement. We should have one of those around here somewhere. Alright, so they give you the biconditional statement. They said, an item is a bracelet if and only if the item is made from gold. So this is giving you an opportunity to translate. They want you to write the conditional, and they want you to write the converse, and then later you'll notice you're going to decide whether they're true or false. So remember, the conditional is just going straight forward, meaning if it is a bracelet, so just put the word if here, take out if and only if, and put the word then in. So if the item is a bracelet, then the item is made from gold. So that's what you go do. If an item is a bracelet, then the item is made from gold. That's P then Q. Well, if you're not sure if that's true, let's go check. Let's go check the bracelets in her jewelry box. She has only one bracelet, and that one bracelet is gold. So we can safely guarantee that if you pick up a bracelet out of her jewelry box, it definitely will be made out of gold because there's only one bracelet. So being a bracelet guarantees that it will be made, that what you grab will be gold. Let's look at the converse. Let's change the order. Let's put gold first and bracelet second. So if an item is made from gold, then the item is a bracelet. Let's go up to our table. Let's look for gold. We have gold right here, and we have gold right here. So in other words, if you grab a gold item, this gold item, sure, will be a bracelet, so that's true. But if you grab another gold item, it's not a bracelet. So you cannot guarantee grabbing a gold item out of the jewelry box will be a bracelet because one of those gold items is a necklace. So in other words, that's a counterexample. So that tells you the converse of the biconditional statement is false. The regular conditional was true, but the converse was not. And if this were going to be a true biconditional statement, it would have to be true forwards and backwards. The conditional and converse both would have to be true. Therefore, this biconditional is false because they are not both true. So remember, it has to be true forwards and backwards. Alright, this is going to be our last example. Go ahead and hit pause and try this one on your own. You don't necessarily have to write it down, but I want you to treat these as 3 different questions. And I want you to decide which parts, A, B, or C, it could be more than one, which ones are true. So take a moment to read the given and decide for yourself. So go ahead and hit pause and try it and test yourself. Alright, so if you did that, you would be reading and you'd say, okay, the first one says, if the tires are old. So that's our first subject that they're mentioning. So that's going to be our P. And then it goes on to say, then Sung knows how to dance. Okay, that's something new, that's Q. Then it goes on to say, Sung knows how to dance. Oh, that's Q again. And then finally it says, then my favorite movie is being shown. Well, that's something new, so that's going to be R. So you'll notice P led into Q, and then Q is used again, and Q led into R. So this tells us they're probably going to be looking for the law of syllogism being used somewhere. So look for an example where they go straight from P all the way to R. So something about the tires being old, and the movie being shown. And if you read, if the tires are old, my favorite movie is being shown. So that tells us the correct answer in this one is going to be B. And I believe B is the only one, but I'll double check for a moment. Yeah, so I just went ahead and checked. That first one is the converse of the original, and the original is the first sentence, and the second one is the converse of the second sentence. But like we said earlier, you cannot guarantee the converse is logically equivalent to the original given conditional statement. So only B is true in this case. So go ahead and try 2 and 3 if you haven't done so already. See if you can decide which ones are true. So go ahead and hit pause and try them if you haven't done so already. And then I'll show the answers. In number 2, you're given an if-then. If geometry is Dale's favorite subject, then the dress is on sale. So if P, then Q. Then it just says, hey, P happened. It's true, meaning geometry is indeed his favorite subject. So what can you logically conclude? What law is that? You should be thinking the law of detachment, because the P has happened. Therefore, we can expect for Q to happen. So look for the answer that says Q is going to happen. In other words, that dress should be on sale. So that's going to be A. So the true one in that one is A. We're not going to negate it because this was given information, meaning it's true. You can't negate it and say it's true because then it would be false if you negated it. And then finally, the dress is not on sale. That's negating the conclusion, and that's not what the law of detachment tells us to do. So go ahead and try the last one if you haven't done so already. Alright, in that last one, I only see one if-then statement, so it's not going to be detachment, it's not going to be syllogism. It just says, if Ruben's cousin is a girl, then the window is above the door. So you're only going to be able to answer this one using logically equivalent statements. So if this is the regular original conditional if-then, you're looking for the contrapositive. That's the only one that's going to be true. So look for the contrapositive. So the window being above the door was the original conclusion, so we need to negate that. The window is not above the door, and that's going to come first. So look for the one that mentions that the window is not above the door. Well, it's not A because it says it is, but it is C. That says is not above the door. So they're negating the original conclusion. Then it needs to negate the original hypothesis. If Ruben's cousin is a girl, so it's going to say the opposite. If Ruben's cousin is not a girl. Notice, It's not saying a boy, even though I agree if you're not a girl, typically you're a boy, I understand that. But we're not trying to use background knowledge, we're just going to literally negate it and say the opposite, or the is not version if it is. If it already was is not, remember, then it would become is a girl. So just bear that in mind. Alright, so that's going to be our last example. I hope this has helped clear up some of your confusions. I welcome you to go back and rewatch parts of the video and hit rewind if you need to. Also check out the help file I posted on our class Edsby page where I wrote down many of these things. So come in to use this to work on your homework. Hopefully these similar questions helped. Come into class next class and with any questions you have on your homework, quality specific questions, and we'll get this done. Take care, guys.